Good evening. Can you hear me?
Yes, we can hear you.
Great. Let's wait another minute or two. Okay, I guess after the Supreme Court decision, everybody's very happy. All right, great. Okay, let's start. So for the next 4 weeks, you're going to do the job and I'm going to enjoy listening to your talks. Before we start, I want to emphasize, I don't see all of you, but especially those coming 4 weeks are essential that everybody shows up in support of your colleagues. Today we'll have Rinat and Zikyan, I'm not sure I'm pronouncing your name correctly, presenting. And for the next following 3 weeks, we'll have 3 speakers each time. I haven't heard from Itai and from Daniel about the topics of choice. I need to authorize those topics, so please contact me as soon as possible. And any questions before we start? Nothing? What do you think about Sean's case that was presented last week? You can open your mics. Can scientists be that driven to bend the rules and cheat? Nobody has anything to say? How do you make sure it doesn't happen to you? I cannot hear. Is somebody trying to talk? You are all muted.
Yeah, I think my internet connection. I think the best advice is just follow what we've been talking about this entire course. You know, keep good lab notebooks, share your work with others, upload your results.
Yeah. And be very careful once you are a PI to know your students. Because some people are so driven that they're willing to bend the rules, and you'll never know. And what is really, for me, so surprising is that it's still happening today, and just be more sensitive to this when you open your Science, Nature, PRL, whatever. Look at the first few pages. Almost every week there is a report of something like this. So scientific misconduct is much more prevailing than what we think. We think that scientists are really pure and they go after the pure science and adhere to the rules. But some people are driven by, they want to have a very successful career and are willing to do everything for this, anything and everything for this. So I'm always surprised when I read about new cases, and I really invite you to be very sensitive to follow up and see, because I think that's also part of the right culture to try to avoid this. Just be aware of all those cases and then teach this to your colleagues and students. Okay, so let's start. Rinat, you'll go first. So you can share your screen and give us your presentation.
You can see my screen?
Yes.
Okay. Okay. Can you hear well and see the screen and okay.
Yes.
Okay, so hi everybody. I'm Rinat Damari, and I'm a student in the research group of Dr. Mayan Sumeniak. So today I'm going to tell you about the paper measurement of the neutrino velocity with the opera detector in the CNGS beam. And this paper is based on the experiment that measured the velocity of the neutrinos. And they found that the velocity of the neutrino is faster than speed of light. Okay, this is the problematic result that I will talk about it later.
Rinat, we don't see your presentation. We don't see your presentation. We see something like open.
We see Open Office 4.
Sorry.
Do you have two screens?
Yes. Okay.
So you need to flip between the two.
Okay, 1 second. And now?
Okay, perfect.
Okay, thank you. So let's start. Okay, a brief layout about my presentation. So in first, I will give a brief introduction about the result, the problem of the result. Then I will give you a background about neutrinos, what are the neutrinos, what are their properties, their physics, their types. And then I will give you a brief reminder about the speed of light, the Einstein theorem of relativity, and why this result challenging the speed of light and Einstein theorem. And then I will present the opera experiment, the tools, the result, the creation of the neutrinos. And then obviously I will talk about the skepticism, why this result is a problem with the physics community not agree with this result, and obviously the skepticism led to some investigations, and then I will give a conclusion about all the presentation. Okay, so as I said before, the result of this experiment is that neutrino velocity is faster than speed of light. Okay, so let's see why it's so problem. Okay, so let's remind what are the neutrinos. Okay, in 1930, Pauli suggested a new particle for explain the beta minus decay, explain the conservation of the momentum in the beta minus decay process. In this process, there is a neutron that decays to proton, electron, and antineutrino. So Pauli suggested there is a new particle that has to be there, and this is the antineutrino, but then the neutrino. Okay. There are three types of neutrino. There are the electron neutrino, the muon neutrino, and the tau neutrino. They can convert themselves to each other, and we will focus in the following slides in the converting of the muon neutrino to tau neutrino. Let's see if I need to say something else. Okay, so the main goal of this experiment was to perform the first detection of neutrino oscillations, and in addition to its main goal, the experiment is meant to determine the neutrino velocity. Okay, and then they found a problematic result that neutrino is faster than the speed of light. Okay, let's talk about the Einstein theory of relativity. After the Michelson-Morley experiment, Einstein realized that the speed of light is a constant in each frame of reference. And in addition, he claimed that nothing is faster than light. Okay, let's watch a short video. I hope it works. You can see that?
Yeah.
Okay, so noisy, I'm sorry. This is the describe the how fast is the light. Okay. You can see my screen. Yes.
We see only the title.
Okay. Yes. Now it's only the title. Okay. So the opera experiment. Let's give some words about it. So opera is the oscillation project with the emulsion tracking. Okay, it's so difficult to say it, but opera is the project. Okay, the experiment actually. LNGS is the lab where is the experiment was performed. CERN is the European organization that performed this experiment, and CNGS is the collaboration between the LNGS and CERN, and SPS is the super proton synchrotron, and this is the particles accelerator. Okay, what is the motivation of this experiment? The motivation is determine the neutrino velocity with high accuracy through the measurement of the time of light and of the distance between the source of the CNGS neutrino beam at CERN and the opera detector at LNGS. Or in simple words, we have the distance, we will measure the time, and then we will calculate the velocity of the neutrinos. Okay, so neutrino is a particle that it's very difficult to detect the neutrinos because he's rarely interact with matter. So how we can create the neutrino? This is the process. So in the SPS, remember the SPS accelerator, they took a proton beam in energy of 400 giga electron volt, and then they directed the proton beam to graphite targets in the CNGS. And then after that, they got kaons and pions, and kaons and pions are particles that are unstable, so they decay to muons and mu-neutrinos. And then the muons and mu-neutrinos, we will get, they got that a part of the mu-neutrinos converted themselves to tau neutrinos. Okay, and then they took the neutrinos, the tau neutrinos, and some mu neutrinos, and directed this to opera detection. This is the figure that describes what I said in the last slide. Okay, we can see here the SPS, okay, the accelerator, the particles accelerator, and then the protons, and they got the pions and kaons. They decay because they are unstable, and then we got the mu neutrinos, and neutrinos go to Gran Sassot, they're the CNGS, the lab. Okay. Okay, so what they wanted to measure, actually in the paper they mentioned the two expression that they want to measure. The TOF is time of flight. Okay, so they measure the time. They calculate the time of flight of the light minus time of flight of the neutrinos, and the difference between the neutrino velocity and speed of light in relation to related to the speed of light. Okay, and this is the length of the tunnel. Okay, the tunnel that the neutrinos go to the detector. Okay, so if they want to measure the time, the difference between the time of light and the velocities, we are accept to a positive number. If we will get a positive number, then we can say that the neutrinos faster than light. Okay, so let's see what they got. Okay, they got positive numbers. They got delta t is a positive number. The difference between the velocities is a positive number. Okay, so they got the neutrinos first on the light. And we know it's challenging the Einstein theorem of relativity. And obviously, okay, what's going on here? What's Q? It's challenging the Einstein, and maybe we need to write all the physics again. So what's going on? Okay, so what is the mistake? The skepticism led to some investigations, and I tell you that they found a mistake. Do you have some ideas what can be the mistake of the experiment?
I know the answer because I lived through this, but let's have students answer.
Okay.
Anybody? What could go wrong? This kept the scientific community at a turmoil for quite some time. They came up with a paper, and it made huge noise, and everybody was talking about this for weeks. And there were a big camp that said it cannot be, but they stood by their results. And then I think independent group was charged in looking at all the actual hardware of the experiment. Anybody has an idea what was going wrong here? What is the measurement? What is the actual measurement? You have seen the formula.
Okay, I will go back the formula.
Here, the measurement is time.
The measurement,
so obviously,
exactly, the measurement
timing,
is time.
Yeah, and obviously the time, the way they measured time was wrong. So, okay, let's keep on going.
Okay. So it's a loose fiber optic cable connecting the GPS receiver to an electronic card in a computer. Okay, this is the mistake. Actually, it was a GPS receiver that detected time and the time of the neutrinos arrived, and the cable was not connected well. So this is the problem.
And how one could basically solve this? Again, what I'm trying to say is that physicists are not that used to the concept of control experiments. It's more prevalent in life sciences, but you could presumably do a control experiment and find this error in timing before you do the actual experiment. So at the end of the day, that was extremely embarrassing. There was a big paper, made big splash, and then they had to retract for this stupid reason that they had not, it was a cable and the calibration was not right, and they could have done an experiment, a control experiment that would show that the timing is wrong. So they haven't done it, and so yeah, that's a good story. It's not scientific misconduct, but it's scientific conduct, I would say. When you design an experiment, you better always think about all the possible control experiments you can do to convince you that what you're going to claim is correct. Okay, well, let me look for... How do we clap? First of all, we can do this.
Thank you.
Some reactions, right? It used to be somewhere else. Well, thank you very much, Rinat. Anybody has questions to Rinat? Have you known about this story? So that was 2012, and it was a huge thing. I remember going through this, and for weeks and weeks, all the physicists around the world were talking about this paper and how that cannot be true until they found the mistake. Okay. Guys, but what I would like to have, if possible, at the end of each presentation by a student, we have a little bit of discussion. So I want to hear what you think about the case, about the presentation. Go ahead.
More verification needed on the physical equipment.
Yeah. Absolutely.
I mean, test the system for.
Yeah, I call it control experiment. Make a simulation of an experiment and make sure that you know how to measure time correctly.
Yeah, something that you know the result and you try to measure the result.
Exactly right. Yeah, in life sciences we call this control experiment. You have a positive control and a negative control. Yeah. Anything else? Other thoughts? All right. So Brina, thank you. You can unshare your presentation, and Zikan, you go next.
Hi, Jim. And the next one, I'm going to give the presentation.
So what are we waiting for?
Can you hear me? I didn't see any.
Can you share your presentation with us?
Yes, of course. Can you see it?
Yeah, great.
Yes.
Okay. So let's.
Okay, go ahead.
Okay, so today I'm going to share a story about the graphene. Tell something about the graphene development process and the controversial Nobel Prize about it. And, I'm going to do this because my last project is on the graphene. Okay, here you can see the structure of the two-dimensional lattice of the single-layer graphene. It's very famous. And here's the contents of today's presentation. First, the introduction. Second is some theory background about the 2D electron gas and quantum Hall effect, like that. Then we will go to share the story about Philip King group and his student Yuan Bozhang, who is now professor in Fudan University in China. And I think some of you maybe hear about this story before, but there are some details that you may not hear before, because I heard a report from Yuan Bozhang, and he told us some secrets or some details about the story. Then I'm going to talk about the controversial Nobel Prize and what we can learn from it. I think all of us are from the physics department, right? So you may be familiar with the graphene. That's a very good system to study some quantum phenomenon, like quantum Hall effect, such kind of things. It was a huge discovery, a great discovery in the physics world. Now I would like to start from the two-dimensional electron gas. It was given in 1970s, and in 1922, the first entire paper about the 2D electron gas was published. And here you can see the structure of the energy band of the 2D electron gas, and because the electrons is bounded in the 2D phase, so the energy band energy level will be quantized, and we will see some quantum phenomena in this kind of system. Before graphene, most of the two-dimensional electron gas experiences observed in the MOSFET system. This is it's a metal oxide semiconductor field effect transistor. Okay, it's a long name. And in this system, Professor Kelsen won the Nobel Prize for the discovery of quantum Hall effect in 1985. You can see this formula here. And this is a very beautiful formula. Why I say this? Because you can see in this formula, everything is related to only two very basic physical quantities. That's the Planck constant and the charging. And the mu here will be a constant, will be an integer in integral quantum Hall effect. And then in 1998, the other three scientists won the Nobel Prize again in quantum Hall effect, but this time they find the fractional quantum Hall effect. That means the nu we just saw can be not only integers but also fractions in some cases, and this fraction is some specific fractions that can be calculated. Here there's another scientist I want to say. His name is Xu Xue, and he's famous of the discovery of quantum anomalous Hall effect in 2013. Actually, the theory of the quantum anomalous Hall effect is given before that, but he's the first one to discover it in the experiment. I want to say him because the other reason is for congratulations, because 2 days before he won the highest prize for scientists in China, given by the Chinese government. And also now I'm in cooperation with. Now we come to the main character of our story, Philip King and Yuanbo Zhang. Philip King is a professor from Korea. Yuanbo Zhang is Chinese. Let's trace the time back to 2002. At that time, Yuanbo Zhang was a PhD student in Philip King's work in Columbia University. And he chose the graphene as his PhD project because at that time, the zero-dimensional carbon bore and the one-dimensional carbon tube has been studied well by other groups, but no one had successfully fabricated the two-dimensional single-layer graphene sheet. And no one knows what can we observe in such kind of system. And this article is published in 2005 by Yuanbo Zhang and Philip King. And let's still go back to 2002. At that time, I say that the most difficult problem is to fabricate the single layer graphene. One article from the Rodney lab inspired Yuanbo to create his experimental methods. In this article, they say that the graphite is actually composed of a lot of single layer graphenes, and this single layer of graphene is like a deck of cards. And if you push it from the side, it will slide apart and you will get a single layer graphene. Okay, so what can you think? What does it remind you of when you consider it as a slide apart? And let's think what kind of thing, what in our daily life is such kind of thing? It's pencil, right? You slide it and you make something exfoliation and leave some very thin materials on your paper. So Yuanbo made some nanoscale pencils, and he thought the main point to get the single layer graphene is to control the direction of the motion of the pencil. So he controls this nanoscale pencil with with some devices and then try to make the single layer graphing. But unfortunately, the success this is hard to succeed, and until 2002, he only got 30 atomic layers thick graphite. However, in 2004, in 2004, Gibbs Group published an article and said they have already successfully exfoliated single layer graphene, and it was published in Science. And this is the article in 2004. And let's see this picture on the bottom right of the slide. You can see that two different ways to do exfoliation. The left one is by the normal force. This is what Gibbs Group used. Use the type to do exfoliation is just to take it apart, and then you will get a single layer. And the second one is the what we have more used to use shear force to push from the side and get a single layer. And this is the first point. This is the first difference between their methods. Second one is that I told you Rainbow use a nanoscale pencil, and you can control the motion of the nanoscale pencil. However, maybe Kim is better in statistical physics, so he didn't control every nanoscale pencil. Why I say nanoscale pencil here? Because let's imagine the exfoliation process in the Gibbs Group. They put a tape on the graphite. It's like there are many touching points between the tape and the graphite. So it's actually they use thousands of nanoscale pencil at the same time. So that's why they succeed to do the exfoliation before Rainbow. And what I told you is the official version of the story. And here I have personal version. So when I was in China, Rainbow gave a speech in my university, and I went to here. And he told us that actually when Gibbs Group published their article, he has already successfully exfoliated single layer graphene, but he was ambitious at that time. He thought he needs to complete all of the measurements and explain all of the phenomena he get, and then publish this huge article. And this article will act like a boom in the physics world. But however, this delay caused them to miss the opportunity to be the first one to exfoliate single layer graphene, and also they missed the Nobel Prize in 2010 due to this. And then I will say something about the Nobel Prize and the 2010. In 2010, the Nobel Prize is given by Gibbs Group for their discovery of for their successful exfoliation of graphene. And when before Nobel Prize community give you the prize, they will publish a document and describe everything clearly in the document, and that document mentioned two articles. Two articles. The first one is published in 2004. The right one in the slide, and the other one is published in 2005. Let's see why I say this is controversial novel. It's because up to now everything is novel. It's a great discovery, and it's a very good experiment. No doubt, and nothing to be controversial. Okay. Let's see where it stands. Let's see this three plots. The first one, let's see the bottom the bottom right one. The bottom right picture is in the article published by Gibbs Group in 2004. You can see in this plot, the scientists claimed that they find the quantum Hall effect in the system. Actually, it is, but you can see that the the experiment is not so perfect. I mean, the data is not so beautiful because the most obvious phenomena in the quantum Hall effect that is the vanish of the XX resistance, but it didn't show in this plot. However, in their article in 2005, that's the top one. Let's say the top one. In the top one plot, it's quite good. It's a very perfect result, and also in the both article in 2005, they find the similar thing. However, what I want to say is that compare these two articles, both of them in 2005, both of them are good articles, and coincidentally, these two articles is submitted almost at the same time. The article given by Kim's group is submitted in July 14th, and the article from Yuanbo is submitted in July 18th. So if the Nobel Prize community regards this as the main reason for their winning the Nobel Prize, so they should also let Philip King and Yuanbo share the prize. This is agreed by almost all of the scientists, and but however, if the Nobel Prize community think Kim's group is the first one who discovered the single layer graphene and make the single layer graphene, actually, I can tell you that back to 1960s, there is another group who successfully exfoliate single layer graphene. However, the size and the property of the material cannot be so good, but they do exactly get the single layer. However, at that time, the measurement method is not so good, and the group who fabricates the graphene is actually chemist is from the chemistry department, so they didn't do some electric field measurement or effect measurement or some transport measurement in the same. So there are some scientists who doubt the decision of Nobel Prize committee. And one of them was the firm. It's showing in the picture. He's showing in the picture, and he said the Nobel Prize community didn't do its work because everyone thinks Philip King and Yuanbo should share the Nobel Prize in that year. What I put here is on the right is what I say, the document given by the Nobel Prize committee. And the other thing that Walter, that's the scientist you saw just now. The other thing that Walter said that he found that in the document from Nobel Prize committee, there is a plot, and is that in the figure caption of that plot, the Nobel Prize document describes the data showing in the plot as a property of graphene. However, in the article published in 2004 by Kim's group, this plot is actually the result of several layer graphite. It's a huge difference because you cannot mix up the graphene with graphite. This is what your price referring to. And, unfortunately, I cannot find that the original version of the document because nowadays the document that's available on the website is only the reversion, and they correct this mistake. When Yuanbo gave us the report, he said that when you start doing some experiments, you might find that 99% of the problems you think about have already been considered by others. But if you persist for 5 or 10 years, one day you will discover something that no one else has thought of. That will be your contribution to the humanity. I do really like this word, this sentence. what I have to say is that you cannot find this sentence on the website because the only version of the report recording is in Chinese, and I translated it into English. Here is the main reference of the presentation. Okay, thank you, everyone. Is there any questions about the presentation?
Great, thank you. So let me comment first. Dickon gave us an example of how to do correct science. This is not an example of misconduct, except maybe for one point. The Kim group was sitting on data and waiting because they were, I guess, perfectionists and they wanted to get better data. Sometimes it's better to publish what you have than wait because there is always competition. People think about similar ideas in different places about the same time. I've seen it many, many times. And the story here points to the fact that if they were a little bit quicker, maybe they could share the prize. The other comment I want to say is this is not the first controversial Nobel Prize. I mean, once the committee makes a decision, then people start to look at and they find many cases. So I can tell from my own field, when Stephen Chu and Cohen Tanuji got the prize, everybody was very upset that Ashkin did not get it. That was for cold atoms and optical trapping. And I have to say that the Nobel Committee did correct this many years later. And Ashkin got the prize almost, I think, 25, 30 years later, just a year before he died. So they did correct this. In the field of ultrafast spectroscopy, Ahmed Zuhail got the prize by himself. The people who were really responsible for making short pulse lasers were Chuck Schenck and Eric Eppen, and they have not been recognized at all. So you can almost find in any prize, you'll find some people who made very, very important contributions that were not included. The Nobel Committee is like any other committee, you know. It's personal views and politics and many other things. Most of the time, I think they get it right, but every now and then you see this type of controversy. So thank you for presenting us this story, and let's open it for some short discussion. Any comments? Guys, I do expect you to participate. Did you know the story? Is it interesting? What do you learn for yourself? What are the conclusions?
A good story. Also, like you said, sometimes you're sitting on good data. And even right now in my experiment, I have some data. It could be better, but honestly, probably better to get moving with it rather than wait around.
Right. And sometimes it's a wrong advice. It really depends, and you don't know. Sometimes you have partial results you want to publish, you get a lot of trouble from reviewers, and you waste time. So this is a very hard call. But obviously this was a very competitive effort. And the guy who got to the finish line first got the jackpot. Other comments? So I've noticed that Netanel participates, but none of the others. Why? Okay, if no more comments, I think we are done for today. We are going to meet next week. I do ask that all of you show up because just out of respect to your colleagues, they've worked, prepared the presentation, be there. Attendance is part of the final grade. And we have lots of good stories coming up, many of them about misconduct. And I'm expecting to learn new things, and you should too. So if no other comments, questions, good night for everybody, and we'll see you next week. Bye-bye. Goodbye.
Bye.
Bye.